And then have you been doing? I'm looking at research project structure. So like on graphical networks or?
I mean, yeah, I guess you're Professor Gonzalez student or Professor Mateos student, so it makes sense that you'd be on GNS. So that's the project you're going to do for this class, or that's for something different?
No, but it's related.
Morning, everyone. Last time we talked about optimization in relative scale. So the L smoothness, in a sense, relative to H is F minus its linearization. It's upper bounded by L times the Bregman divergence between the 2 points Y and X. This is a way to generalize the normal definition when H is the Euclidean distance. And the other notion is mu-strong convexity. When we say F is mu-strongly convex relative to H, it means F minus its linearization is lower bounded by mu times the Bregman divergence. So these two generalize the normal definition for L smoothness and mu-strong convexity whenever you change H to the Euclidean distance. And we also talk about one algorithm, that is the Primal gradient method with the reference H. In this algorithm, we try to find the minimizer to minimum of f of x when x is in the constraint set Q. So this algorithm is quite simple. We basically just linearize f and add this is like the quadratic function we usually have, but now we just use Bregman divergence. this is algorithm, and we gave the convergence analysis last time. But to do this algorithm, there is one important iterate, that is to solve this argument, right? But previously, when h is the Euclidean distance, this is just a quadratic function. So we can easily find the closed form solution. That is the projected gradient step. But when h is not Euclidean distance, we need to solve it case by case. It depends on what h is. So let's see two examples. These are the examples we have seen last time for showing L smoothness in the relative sense. The first example is when h of x is as follows. Last time we showed that if f is twice differentiable, and the norm of the Hessian is upper bounded by a polynomial, an R-degree polynomial in terms of the norm of x. This is a matrix norm, this is a vector norm. And when the function, the polynomial PR satisfies when this inequality holds with a certain L, then we say that f is L smooth relative to this h. Okay, this is the example we gave last time. And now let's see when the h here is specifically this one, then how we solve this subproblem. Okay, so we want to solve the following subproblem. Okay, so to solve this one, we can always solve the unconstrained one. Change this to x belongs to Rn, and then we can do the projection. So, so it boils down to solve this problem. We can abstract the linear term in x as this inner product c times x, right, and ignore the constant term. Right, so this linearization and this linearization in the linearization in the Bregman divergence can be written in an abstract form, the inner product C with X for some certain C, right? And what's left is just a function h of X in the Brakman divergence. H is just this portion, the sum of the two. Okay. So let's see the optimality condition to this one. We have shown how to take the gradient of this one. So using the formula we had last time, this is the optimality condition. And from here, because this is a scalar, so this equation basically means X is in the direction of C, right, with a certain scalar. So we can say X is some theta times C. For simplicity, let's use minus theta times C. And theta is the negative. Okay, then if this C is 0, then we can easily take X to be 0. If C is not a 0 vector, then we can plug this formula back into this equation and simplify it. So what we have is the constant should be 0. Okay. This is by plugging in X to be minus theta times C. By plugging in X to be minus theta times C, then here is the coefficient in front of C, right? This one needs to be 0. So this is a univariate equation in terms of theta. So just need to solve for finding the root, right? You can use maybe Newton's method, for example. So this is a way to solve problem here. And with this, we can really do the iterate and use the primal gradient method to find the solution to this one.
Here we have the linearization between x and xk. Am I right? But here we don't have xk.
Here I ignore that xk. It's not important because xk only shows up here and it's a constant. When you take inner product with c and xk, it's constant.
So is the linear product between c and x stands for the linear form, and that's the
here is h of x minus linearization, right? The C this is a C. Okay. C is this one divided by L. Because this L also multiplies H. Yeah. C is this divided by L. Second example is the optimal design. We also showed that this is the function f in the optimal design is one smooth with respect to a certain function h. The f we had we showed that this f is 1 smooth relative to h on the unit simplex. And now let's see how we solve the subproblem in this case for the optimal design. So we want to solve the following subproblem. Right, this is a subproblem. Here is just the h function, and we also have the inner product term. So, the optimality condition. First, we need to satisfy the constraint here. X has to be non-negative and summation of the elements should be 1. These two are the constraints in the simplex. And the other one is to write a gradient to the Lagrangian function to be 0, right? And here we associate this constraint with a Lagrange multiplier zeta. So the gradient to the Lagrangian function is c minus this basically, this x inverse just means x1 inverse xn inverse is a diagonal matrix, and this one is a all one vector. So this is a matrix. This is a vector addition. This is also a vector. This is a first order optimality condition to the Lagrange function, setting the gradient to be 0. And from here, because this is basically telling you the operation in each element, in each coordinate, right? So for let's call this C to be a vector C1 to Cn. And this is telling us xj right? And because, so this satisfies, of course, this satisfies the non-negative constraint here because zeta here is also non-negative.
What is zeta again? Sorry.
Zeta is the Lagrange multiplier associated with this one. No, zeta is not non-negative, zeta is unconstrained. So this is the solution to this one, right? For each element-wise. And then we need to solve this equation to find the zeta. Summation of xi's, xj's should be 1. Oh, sorry, this is 1. So we need to solve this equation because this is also similar to what we have here. It's again a univariate equation in terms of zeta. So we need to solve this one. In the interval that zeta is greater than or equal to minus cj for every j, right? We need to find the zeta in this interval. If you can find a solution, then you solve the subproblem. Otherwise, there's no solution to it. Right. Okay, so these are the two examples to solve the subproblem. Now we finish the primal algorithm. let me present you a dual version of the algorithm.
Excuse me, Professor. CJs are given there or we have to calculate it?
CJ have come from here.
That's the formula.
Yeah. This algorithm is called dual averaging. This is not new in this context, in relative scale. It already exists in the normal setting when you use Euclidean distance. What's interesting in the algorithm is that from the name dual averaging, because this is taking average among something, so this is where averaging comes from, and dual comes from the fact that here we are averaging basically the gradient. But here, what's important in this linearization is a gradient. It's the gradient f at the point xi. And if you remember from the lecture on mirror descent, we interpret this as the dual variable, right? Because in mirror descent, we view x as the variable in the primal space, and the gradient of f at a certain point x is in something in the dual space. So this is primal and dual. So in the previous algorithm, we call it primal gradient. We do not view the gradient as something in the do space, but we just view it as an operator, an object in the primal space. But here, what's important in the linearization is the gradient, and view it as the one in the do space. So here, summation AI plus 1 times this gradient is an averaging already. If you divide it by the summation of if you divide by, again, the summation AI plus 1, this is an average, right? This is a combination of the gradients. So it's called do averaging. And another thing that's important here is in the algorithm, we also need to use the strong convexity parameter mu. But in the primal algorithm, we only use the L, the smoothness. And also the initial point is special. This is, usually people call it the H center in the set Q because this is the minimizer to the function H. Suppose your H is the Euclidean distance, then this x0 is just the origin, right? This theorem tells us two interesting cases. One is when mu is greater than 0, then this is the convergence rate you're going to have. This is like a linear convergence. And this is a case when actually mu is indeed 0. Because when mu is 0, you can take this mu to be 0, so this is an upper bound on the strongly convex case. This is just convex. In this case, the convergence rate is 1 over k. But when mu is positive, when it is indeed strongly convex, we use this one. This gives us a tighter bond. let's call the function in this subproblem to be psi sub k, and let's call the minimum of this function for x in Q to be psi k star. So this is the function value that we obtain in the subproblem. And by definition, xk plus 1 should be. Oh, this is xk, because here we change the index from this k to be k minus 1. So this is xk plus 1, this is indeed xk. But this function here is actually psi k plus 1. And also clearly, psi k of xk is psi k star. So because the function f is mu strongly convex relative to the function h, so this portion here, this part, by mu strong convexity, this is greater than or equal to f of x. Right, so we have because for each I, this part is greater than or equal to f of x. So in the end, this psi k,
Less than.
yeah, the other direction. It's less than or equal to f of x. So if you sum everything together, then factor out f of x, in the end you're going to have this inequality. And this is because psi k star is the minimum. And ak here is basically the summation of the ai. Because ai is given here, so it's a geometric sequence. And we can indeed compute the capital AK. This psi k, here we have h of x, and in this linearization part, this is just a linearization, and here, again by the definition of Primal divergence, this is h of x minus linearization. Right, so here is a linearization, here is another linearization. So this psi k of x can be rewritten as right, so psi k of x can be rewritten as 1 plus mu times capital AK times h function, this h of x, plus a linear function, right? Because here in for every I here you have mu times h of x, and if you do the summation, this gives you mu times AK, and the other one is coming from here. With this observation, we can say that psi k of x and this part, 1 plus mu AK times h of x, these two, if you do the Brakman divergence, these two will give us the same Brakman divergence, because this linearization will be cancelled out, right? because if you do the calculation, the linearization will basically perform as this h. So linearization minus this linearization is 0. It goes away. Right. The first identity is just the observation. The Bragman divergence for this function is the same as the Bragman divergence for this psi k. Right. This is what we just observed. And this is just by definition of the Bragman divergence. Psi k of xk is what we call psi k star. So we just need to show this part is ignoring the negative sign. This part is non-negative. And this is because xk is the minimizer. This is psi k. Because xk is the minimizer, so by the automatic condition, this should be non-negative. Right, so we can ignore it. Gives us the inequality. The first identity here is by definition, and the second one comes from the definition for psi k. If you do the next iterate, psi k plus 1 only differs from psi k, the additional term multiplied by ak plus 1. Right? So it gives this additional term here. And here we just take x to be xk plus 1. Right? From here to here, we are using this inequality. So take x to be xk plus 1. We have psi k xk plus 1, and it's greater than or equal to this Bragman divergence with psi k star. So psi k star comes from here. The other part is here. And here we just copy from what's above. And this mu part also comes from what's above. Right? And now from here we are going to show the recursive formula. But first let's note one fact. Okay, so basically in this line we are calculating what this quantity is. So by definition, mu times mu times AK plus 1 plus mu times capital AK gives us this part, mu times capital AK plus 1. And using the result for this one, using this line here, the calculation for AK, we have this formula. And if you take a closer look at what this is, by the definition of AK, it's just giving us the L. This is just L. Okay, right. Yeah, this is just L. So it means this part is simply just L. So here I'm just continuing from this line to here. Just copy everything what we have so far and just replace this portion by L. Noting that this perfectly gives us the inequality we need for the L smoothness. So this gives us the lower bound AK plus 1 times f of x k plus 1. And this is a recursive formula, right? Here k plus 1, here is k. And then we can use the normal trick to do the summation and then simplify a lot.
The fact is not clear for me. Would you please explain one more?
Which part is not clear?
The fact. No,
This fact?
yes.
Which inequality you don't understand?
How do we?
This is using the calculation here. And the last line is using AK plus 1, definition of AK plus 1. Over there.
Right. Yeah. Okay. And also another question. In the theorem, the tight bound is for the strong convexity, and the other one is for general convexity.
This is a this holds in general.
Yeah.
Because this is non-negative. This is the minimum. H of x0 is the minimum by definition here. Right. So h of x star minus hx0 is always non-negative. So this is just telling that mu divided by this quantity is upper bounded by L minus mu over K.
Actually, when we have just convexity and mu is 0.
When mu is 0, then take the limit of this one. Let mu to be 0 goes to 0, then the limit is this one. But in general, it's always upper bounded by this.
I imagine that when we plug in the mu equals 0, we have to reach to the second one. So So it's not.
This is for. But you can, to be rigorous, you need to. You can also take. You can take the limit, right? You can take limit. Mu goes to 0, and this one will goes to this one without mu. But so writing the second bound here is just for you to simply consider what the case is when mu is 0. Just take mu to be 0. L over k is your convergence rate. Yeah. But this holds in general. In general, mu doesn't have to be 0 for this to be true. Can you see how this is true?
When we take the limits of mu over 1 plus that equation, it should go to L minus mu over k. Am I correct?
Yeah, but do you know in general why this is true? When you don't take the limit when mu is positive, why this is true?
No, it's not.
Just do the Taylor expansion of this one and keep the first term. Right? The first term is just linear. This one times k. Right?
Oh, perfect.
Yeah.
Perfect. Thank you.
Okay, so now we need to sum this inequality, but before summing this one, we need to have the base case, that is when k is 0. Right? This holds for k greater than or equal to, this holds for k greater than or equal to 0. But we also need to have a bound on phi 0 star.
One second, Professor. I want to take a picture.
What is H star?
Oh, this is h of x star. X star is the minimum to f. Yeah. This is f of x star. Because here we are minimizing just f, not f plus h. K 0, phi 0 of x is just h of x. Because when k is 0, this is from 0 to minus 1, so this part, the summation doesn't exist. Phi 0 is just h of, phi 0 of x is just h of x. And
Yeah, why the last one is greater than?
here, this is by the L smooth inequality. Linearization plus L times the Brooklyn divergence greater than or equal to the function value at this point. Here is not 0. I think this should be 1. Here what I do is to, basically this is to redo this general proof for the case when k is 0. But I don't see why k is 0, when k is 0 this is wrong. But anyway, this must be true when k is greater than or equal to 1, and for the special case when k is 0, this is also true. But it can be simplified, can we combine the two proofs as one, just this case, the general case for every k greater than or equal to 0. I don't see why this is wrong when k is 0, but I don't remember why I separate the proof into two parts. But at least this argument is correct. This holds for k greater than or equal to 1, this is true when k is 0. For this one, the first line is just by definition. Right, by this definition, plug in k to be 1, and this is phi1 of x1, right? This is by definition. And from here to here, we are using similar techniques as there. This is by strong convexity, the mu strong convexity relative to h. And here, we are using convective function h. H is convex, right? This is by convexity. And this is because, actually, we don't need to do this. I think we can directly, because h of x0 is the minimum, so h of x1 is always greater than to hx0. And so we can directly go to the last line. This,
Sorry, I think
which
the
part
only
is
the
wrong?
only reason that we might not be able to, I think, is maybe the step where we go from mu plus 1 plus mu ak equals L. Does that still hold if for A0? Because A0 would just be 0.
Where is A0?
So, well, you have mu ak, so the term where we say note the fact.
I mean, here?
Yeah, wouldn't ak be...
Capital A0.
Yeah, capital A0 would just be 0, I would think. So then it
No
would,
definition.
Yes, A0 should be 0.
so then would that fact not hold, so we wouldn't have L, so we couldn't use the inequality at the end? Because then it would be 1 plus...
If this is 0, then
Oh wait, no, it would still hold, never mind.
yeah, this should still be true.
Yeah, it would still, yeah, you're right, I'm sorry.
I don't see why it's not true, but this is always true. And
Yeah.
in the end, you can put them together, right? Because this is also, because here we know phi 0 is h, so this is also phi 0 of x 0 is, you can also call it phi 0 star. So these two can be combined, I think, in the end. Yeah. So in the end, what's wrong here?
But the inequality should be less than or equal to f1. I mean the linear term plus the mu be less than or equal to f1.
Oh, yeah, let me see. Uh, okay, A1.
A1 would just be,
1 over L minus mu.
so that would still work for equaling L, so that's not the issue.
Yeah, this is, let me see. I mean, why this is pretty not good, right? Oh, yeah, we cannot skip this line. I see. We still need this line. This is H. This line is important. Actually, what we have here is the linearization. So I think I skipped a few lines here. So I skipped some derivation between these two lines. Let's do it here. So from here to here, so this line, the second line, is equal to linearization h x1 x0 right? It's a linearization of this. And we want to show this line is greater than or equal to, this is greater than or equal to. Want to show this line is greater than, here, this line is greater than or equal to this line. So it's equivalent to show that putting this term to the left, so we have fragment divergence again, right? x1, x0. But putting this one to the left, right? When you do the subtraction, you have this fragment divergence. And you want to show this one plus A1 right? This is what we want to show. Right? Just do this term to the left, and h of x1 minus this linearization gives you this fragment divergence.
To which left?
You want to show this line is greater than to this line. I'm showing you this,
Oh, okay.
this derivation here, right?
Okay.
And I'm saying this line is equivalent to this line.
Okay.
So I want to show first line greater than or equal to this line. To show that is equivalent to show this one. Right? And this A1, we just figure out A1 is 1 over L minus mu. Right, rearranging the terms, this is equivalent to this one. So if you can show this one, you can also show this line. Okay. Let's simplify here. This is just L over L minus mu dH. Right, and now we can cancel out all the 1 over L minus mu because it's always non-negative. It's always positive. Right? So this is the smooth inequality, the L smooth inequality. So since this is always true, then all the ones above are always true. Right? So this justifies this line here. We cannot skip this line. It's very important.
Excuse me, the first one, isn't it L minus 2L? But they don't cancel out.
Which one?
Here? Yeah.
Here we are factoring out all the coefficients for the Brakman divergence. Here is the 1, and here is, okay, it's plus, yeah, you're right.
Oh, yeah.
This is mu times A1 is this
Yeah.
part.
No,
Yeah. Right, so to make this proof formal, we need to go from here to above, and then justify this line here. Okay. This is the part that makes the case 1, case 0 different from the general case, because in there we don't exactly use the A, but I think this. If you figure out what is wrong here for the case 1, case 0, please let me know. But at least this proof should be correct. Right? That holds for k greater than to 0, 1. This is the case 1, case 0. And now all the inequalities are in the same format. They're just psi k plus 1 star greater than or equal to the right hand side. And then summing them up, you will have this inequality when you sum up. And here, from here to here, we are using the fact we have just shown an inequality here that I erased. A phi k star is less than or equal to h of x plus ak f of x for any x. And if you take this x to be x star, then so here this is so this is greater than or equal to AK minimum f of xi right? This is greater than to AK times the minimum. And let's take x to be x star. So we have AK right, and then we divided the inequality by AK. It gives this inequality because this is mu over this quantity is just because this quantity divided by mu, this is just AK. It's equal to AK. Right, so this concludes the proof. And the last inequality is just by expanding this this term.
Excuse me. All the formulations is clear. I agree with them. But could you please explain one more time what makes the k equals 0 a special case?
I don't know. I don't know why it's special, but I just forgot why I separated two cases. But that one should be true, at least for k greater than to 1. For k0, I can't see right now why it is not true.
Is it just because we didn't define capital AK at 0? Like if we say it's 0 at k equals 0, then it would still hold. But
But
I don't know, like just because if it's AK plus 1 or A1 equals 1 over L plus mu, then it would trivially hold. Not trivially, but it would be shown to hold if AK equals, or if capital AK equals 0. The only thing I'm thinking of is that it just wasn't defined for 0. I'm not sure.
Yeah, when this is 0, it's just the mu plus 1 over A1. And A1 is 1 over L mu, so this is just L.
Yeah.
Yeah. I think this might be true because here we do this basically the same calculation here, right? Do it again here, just in a different form. I think yeah, this should be true when k is 0. Yeah, but in the end, the conclusion are the same. This is the same conclusion as this one by taking k to be 0. I think this proof can be absorbed into that proof. But anyway, the conclusion is correct, right? Convinced that this is true, right? Okay, so this gives you the convergence rate if you use the dual averaging. It should be the same convergence rate. And also, if you, let's see what it reduces to when we take h to be the Euclidean distance. So for example, in the convex case, when mu is 0, its rate becomes L over K times h here is the Euclidean distance, right? So h of x0, this is the minimum, so it's 0. And this part is just the 1 over 2 x0 minus x star. Right, so this gives you the normal convergence rate in the Euclidean setting. Okay, I think that finishes the lecture on relative scale optimization. Any questions?
Excuse me. So is there a generalization for what we have learned before?
What you generalized is the definition for L smooth and mu strong convexity, and also here you use the h function instead of you are using the distance generating function instead of the Euclidean distance, and also the way you need to solve the subproblem is not easy, right? Before you have closed-form solution, but now you need to, for example, you need to use Newton to solve the root. Yes.
So my question is actually related to that. So you're not going to get the exact solution if you use another iterative method within this. So you'll have some error bound there. So how do you factor that into a proof like this when you're trying to
can turn this to be, because this is exact solving the subproblem. With that additional inexactness, you can turn it to be, for example, a variant of the inexact proximal point method.
Okay.
You can use the inexactness in the framework to handle the inexactness in the solution to the subproblem.
Yeah, that makes sense. That should have been obvious. Sorry.
Yeah, it's not obvious, but yeah, it requires some development. The benefit of this algorithm is that in many cases, for example, in in the two examples we gave, the general case where the hashing of the f is bounded by some polynomial, and also in the d-optimal design. In these two cases, you do not have a uniform L in the Euclidean setting, right? But whenever you change the reference function h to be some specific one, you can find a uniform smoothness L or mu, and that facilitates many computation. So this is one way to avoid using a uniform L, but this is in the sense that we do not use Euclidean distance. In real applications, there are some other cases that we also want to avoid the general L, the uniform L. So this motivates the next lecture. So it's another way to avoid the L. This is randomized coordinate descent method. Okay, let me do a quick motivation here. So suppose we want to minimize f of x. And now this n is very large. N could be million or maybe tens of millions. So in that case, you never want to solve the problem by using proximal or project gradient method, because that will take the full gradient evaluation, right? Then it takes, because gradient evaluation and function value evaluation, or even the directional derivative evaluation will take order n computations, right? And because n here is huge, could be million or tens of millions, this could be very expensive, even if you do one iteration. So we want to, the idea is to break this long vector. This is an n-dimensional vector. We want to break it into small pieces. Maybe for example, when n is 1 million, maybe you want to break it into a few pieces, and every piece is just a vector of dimension 1000. And every time you just update a portion of its gradient. So you just update 1000 elements every time. But this could be done in many fashions. For example, you can do it in a cyclic way, right? You update this portion, but keep others the same, and next time you just, with this updated information, you keep this fixed and others fixed, update the second block, right? You can do it in a cyclic way. But the drawback here is that there is no theoretical guarantee for convergence if you do this cyclic way. This is like the Gibbs sampling, right? You just update in block by block. Or you can choose the block that gives you the maximum norm of the gradient. So for this part, I have a gradient. This part, I have gradient. I can evaluate the norm of the gradient. And then I choose the maximum one. This can give you a convergence guarantee, but it's not good. In that case, the theoretical guarantee is worse than if you do the full gradient update. So these two methods either have a drawback in the theoretical guarantee or have a drawback in the real computation, because we need to do a full gradient evaluation, right? So then it comes to the third idea. Then I may choose one of the blocks randomly. I choose it with certain probability, associated with each block a probability, right? Maybe I choose according to this probability, and then I can do the update. So next time I will show you this method really has a convergence guarantee, and in practice, it's much faster than every one we mentioned before.
So when you say randomly, I'm guessing the first way to analyze it is with replacement, because that's easier. Is there a convergence guarantee without replacement?
What do you mean by without?
So for instance, like sampling without replacement would be doing a sweep, but each time you scramble it before you do a sweep with Gibbs sampling, versus without replacement where you, or with replacement where you could potentially pick the same block multiple times before you see another block.
You can do it. You can sample it multiple times.
Okay,
Yeah.
that's fine.
That's called the replacement, right?
Yes.
Yeah, yeah. You can do it in the replacement fashion.
Okay.
Put this to the left. Take us to next sorry. Put it to the left.
I just have one quick question on the project. So I already turned in my proposal, but I just want to make sure before the deadline actually passes that what I want to do is A, sounds feasible, or B.
Oh, I will take a look at your proposal and
Oh, okay.
yeah, I will give you some feedback.
Okay, okay, thank you.
Goodbye, Professor. Goodbye. Goodbye.
What?
So that was carried from the
I wouldn't think about When did you get that?
last So I mean, it could have been worse getting from it.
You're doing great.
Yeah, that's awesome. Really, I think it's like,
Really?